So this was the rest of the lecture slides we didn't get to cover in class. Um, yeah, for emphasis, the worked example problems on your announcement will cover what you need to know that will be on the test. So if you're worried, you can listen to the rest of these video lecture. I think I'll try to make it in 15-minute sections and upload them. Okay, so starting off from the risk assessment slide is the one we got to last. The probability of dying if you play high school football is about 10 per 10 million player days of exposure. That is, for each 1 million players playing 10 days of football, about 10 deaths due to football-related causes can be expected. The next one gives you the risk of getting cancer from asbestos if you attend a school in which asbestos is present for 10 years. It was about 5 per million. That is, for 1 million students attending a school for 10 years, about 5 can be expected to die due to asbestos-related causes. If we ban asbestos from schools, which we do, shouldn't we also ban high school football? So this is just a matter of calculating the statistical risks of football versus asbestos, and as you can see, we allow much more riskier and dangerous activities without the use of statistics. So similarly, auto accidents kill between 40,000 and 50,000 people in the US each year. Crashes of all scheduled US air carriers have killed between 0 and 550 people per year in recent years. Which do you consider to be safer? Traveling by cars or traveling by plane? So as you can see, most people feel planes are very dangerous. The whole it can crash and you'll fall into your death from a high altitude. But apparently car accidents are much more prevalent. So driving in your car is much more riskier than traveling by plane. So the third risk assessment is few of us would leave a baby sleeping alone in the house while we drive off on a 10-minute errand, even though car crash risks are much greater than home risks. As we just mentioned in the previous slide, car accidents happen quite frequently. In fact, it is against the law to leave a child that young at home. So take it as a fact that the probability that the baby will be injured in the car is very much higher than the probability of any harm at home in the same period. Would you leave the baby alone? If not, why not? So, yeah, statistically, nothing's going to happen to your sleeping baby. So if you need to go do laundry somewhere, you wouldn't take your baby with you. But if you feel like when you go into the store, you have to take your baby with you because it's child abuse, blah blah. But just from the statistical viewpoint, it's much more dangerous to take your baby. So here's another framing question. I'll deal with framing. Linda is 31 years old, single, outspoken, and very bright. She majored in philosophy. As a student, she was deeply concerned with issues of discrimination and social justice, and also participated in anti-war demonstrations. Please rank order the following statements by their probability of being true, using 1 for the most probable and 9 for the least probable. So Linda is an active feminist. Linda is a bank teller. Linda is a bank teller and an active feminist. So if you ranked C above B, that Linda is a bank teller, and an active feminist, you're committing a conditional or a combined probability error. And Linda being an active feminist is representative by these characteristics, discrimination and social justice. So you might think she is a feminist, but that probability is dependent on the natural probability of the population. So how many feminists are there in the population? So we're going to go further into that. So the idea of representativeness is that Linda appears to be a feminist, as those characteristics I pointed to earlier. So anything that describes her as a feminist is regarded as more probable than anything else, and consider the and conjunction rule of probability. So for non-independent outcomes, one outcome depends on another. You have these joint probabilities. Probability of A and B equals probability of A given B times the probability of B, or the probability of B given A times the probability of A. So now you know this is where we get our equations to those problems I have on the announcements. So that's the start of what is probability A and B. It says that two outcomes occurring together is equal to the probability of one outcome multiplied by the conditional probability of the second outcome that's conditional upon the first outcome. Very complicated. It reduces to any probability of A and B is given by these equations, and which equations you use is depend on which one you already have to solve for the other one. So you're probably given A, or you're probably given the probability of B, and you'll solve for the other one. So it depends on what we're giving you. For independent outcomes, where one outcome does not depend on the other, you have these differences. Probability of A and B is just the probability of A times the probability of B. So you can think of this as two coin flips. They're independent, so it's just probability of 0.5 times 0.5. This says that the two outcomes occurring together is equal to the probability of one outcome multiplied by the unconditional probability of the second outcome. So this problem is much simpler than the previous one. Right? So back to the Linda problem. The probability of A is that she's a bank teller, B that she's a feminist. The probability of A and B is less than or equal to the probability of A, and the probability of A and B is less than or equal to probability of B. So why do people fail this test? So the idea is that for any given probability that she's a bank teller and a feminist, it could only be equal to or greater than whether she's a bank teller or whether she's a feminist. But when you combine them, the probability is much lower, or equal to the max. So here's the explanation behind that. Consider all bank tellers in existence. 20% of people are bank tellers. So the probability of Linda being a bank teller is 0.2. Or, in our case. Now what if all bank tellers were feminists? Then the maximum it would still be is 0.2, right? So going back to this, the probability that she is a bank teller and feminist is conditioned to the maximum of either one or the other, the lowest of those two. So if even one bank teller is not a feminist, then what happens? Then that the probability that Linda is a bank teller and a feminist decreases. And vice versa for feminists. So joint outcomes always occur less often than they constitute individual outcomes, unless one other outcome has a probability of 1, which is certain to occur. Yet most people fail this test when represented with a stereotypical description that represents a person. So some Kahneman won a Nobel Prize for this research on framing. The stereotyping simply reflect an inadequate understanding of probability and the joint probability rule. So Kahneman says yes, and he got a Nobel Prize. So we're really bad at probability. So if you're having problems understanding this, it's very abstract, and we seem to be naturally not so great with it. So more on conditional probability, relationship between marijuana use and hard drug use. Marijuana is a gateway drug. Marijuana as a gateway drug theory is true. So if you've heard about this idea that weed leads to other things, this is going to be proof against that. So this was a Newsweek article in '98, reported that the data says 80% of heroin users have used weed, and doesn't indicate the strong relationship between smoking weed and using heroin. Does this necessarily indicate a causal connection? So 80% of heroin users, seems like a lot of heroin users have used weed, and maybe they have moved on to harder drugs. Or that's the premise for the gateway drug theory. So how do we solve that? The relationship between marijuana use and hard drug use. Let A be the event that a person has smoked marijuana, so probability of A. Let B be the event that a person has smoked heroin, probability of B. We have been told that 80% of heroin users have used marijuana, so hence the probability of A, marijuana use, given heroin use is 0.8. So remember, going back, if you're given some parts of the equation, you pick which one to use. So for this one, you're given A, given B, so the other probability is multiplied by the probability of A, right? To assess the gateway theory, don't we really need to know how many marijuana users go on to use heroin? That is, shouldn't the cause precede the effect? Right, so we actually want to know what is the probability of B given A, or what is the probability of using heroin given that you've smoked weed, which we don't know. So here's how we're going to solve it. Do we need more data to assess this issue? Yes. So what's missing? Remember, the second part of the equation is we need a probability of one or the other. In this case, we probably need the probability of A. So specifically from the joint probability rule for non-independent outcomes. So remember, independent is just probability of A multiplied by the probability of B. But non-independent, you have that more complex equation, which is it's the same equation, just the things are flipped. So yeah, if you multiply this probability of A to this side, as solving for algebra, you'll get back that original equation that you saw a few slides back. So the main point is we need to know what is the probability of A and what is the probability of A and B to solve for the probability of B given A. So probability of A and B are easy. They are just the prevalence rates in the population. So the probability of A is 0.5 and the probability of B is 0.10. So A, remember, is marijuana use, B is heroin use. So these are the unconditional probabilities of a randomly selected person having used marijuana or heroin. Just that means they're not conditioned on each other, so independent. Next slide. So you can use the equation that I have. For me, that seems the easiest case because you're given a bunch of numbers, you just plug it in. But Robert recommends using the table format, which is a second set of the same solution, which might be easier, and you can choose which one you want. So we know the prevalence rate. Suppose we have a hypothetical 1,000 users. We know a prevalence rate for both marijuana and heroin use. So we can put them in a table. 50% have used marijuana and 10% have used heroin. These are the marginal probabilities of use because they are placed in the outside margins of the table. So we know 50% of people have used marijuana, so we want to multiply that by 1,000, and we get half and half, right? 500. And we know that 10% have used heroin, so going down, 10% have used heroin, and 90% have not. So we have these outside solutions based on the given prevalence rate. So the first thing is to set up this table this way. So if we now only have one additional piece of information about the table, we can solve for all 4 cells of the table. We know from Newsweek that 80% of all heroin users have also used marijuana. That is, of the 100 hypothetical users who have used heroin, 80 of them would have used marijuana as well. So 100 times 0.8, you get 80. So now you have that cell. So all you have to do is add them up, right? So what's this? If 80 have used it, 20 has not used it. If 80 have used it here, we know that 42 has not used it, to add up to those totals. So once you do that, it's really easy, right? Now you have solved for all your given probabilities. So now what percentage of all marijuana users have also used heroin? So this is given by the probability of heroin given marijuana use is 80 divided by 500. or about 16%. So this is just wording. You get a lot of questions like this, right? What percentage of all marijuana users? So it's across this row. So if you use marijuana, it's top row, right? Not the second row, because that's people who've not used marijuana. So just top row, and have also used heroin. So yes, yes, this is square. So the opposite would be what percentage have not used it. So yeah, so we're only focusing on this cell and across this row. So so this is 16% who have used marijuana has also used heroin. So this is hardly an overwhelming number, since 10% of all water drinkers have also gone on to use heroin, and 10% of all children who attend school have also gone on to use heroin. Or even better, it turns out 100% of all heroin users have also attended school. So that's a joke. So causal inference. The probability of heroin given marijuana use is called a prospective probability, whereas the probability of marijuana use given that they've taken heroin is called a retrospective probability. Guess which is better for making a causal inference? Of course, the prospective probability, right? Because they're saying people who use heroin have also used marijuana in the past, so this is retrospective. And when we want to make a causal inference, so something caused another, we can't say that, oh, you did this in the past. It has to be forward thinking. So the first one, the prospective probability is stronger. So given that you've used marijuana, how likely are you to go on to use heroin? So it's gone on a little long. I'll probably cut it off at 30 minutes. So risk assessment, I'll cut it off now and then release a second video on the rest of this.